Yes, thanks again for accepting to participate to this webinar session in the framework of AI Chair OceaniX. So today you will talk about an extended version of physics-informed neural network with a generalized space-time domain decomposition based on a deep learning framework for nonlinear PDEs. So I don't know how long you plan to talk, but
it would be around 40 to 45 minutes. So there will be around 5-10 minutes. We can have a question answer session.
Oh yeah, that's perfect. As you just said, we will have some more time for questions from the audience. So okay, I think we are already 21 participants, so maybe we can start. I leave you the floor. Yeah.
Okay. Thank you for the introduction, and I would like to thank the Professor Ronan and his group for inviting me to present my current research. So, good afternoon, everyone. And today, my topic of presentation is the extended physics-informed neural network, or in short, XPINNs, which is basically a generalized space-time domain decomposition technique. So here is an overview. So first, we'll discuss the physics-informed machine learning techniques briefly. And in particular, we will then jump to the physics-informed neural network, or PINNs. And then we will discuss two domain decomposition-based approach, conservative PINNs for conservation laws, and then more general extended PINNs or XPINNs. And finally, we'll see some results. So, so first we'll discuss about the traditional approaches which we are using for scientific computation. So these approaches for scientific computation has undergone remarkable progress, but they still operate under very stringent requirements. So more often or less, they require precise knowledge of the underlying physical laws. They also require precise knowledge of boundary condition, initial condition, for simulation, for the simulation, and often they needs a time-consuming workflow such as mesh generation and long-time simulation. So on the top of this limitation, the simulation for real observation data for ill-posed inverse problem can become very costly, where simulation need to be performed multiple times to either discover missing physics in the model or calibrate the free parameters. So basically, we are seeing this regime shown here in a green zone. So this is actually an ill-posed inverse problem where this is a very interesting regime where we know some data, uh, and at the same time, we also know some physics. So due to such gappy or noisy data, uh, or incomplete knowledge of the underlying physical laws, the traditional method faces difficulty. So it's really difficult to solve this kind of problem using traditional methods. So in this case, the physics-informed machine learning can play a bigger role to solve such problems. So what is physics-informed machine learning? So it is basically it's a dictionary definition. So it's a process by which the prior knowledge stemming from the observational, empirical, physical, and the mathematical understanding of the underlying model can be leveraged to improve the performance of the ML algorithm. So it's a machine learning algorithm. So by incorporating the physical laws in the machine learning, physics-informed neural network seeks to build scientifically accurate predictive models, accelerate the training of the machine learning models with increasing data efficiency. That means by using very few data points, and increase interpretability to make ML model more robust and trustworthy. So the next question, general question, is how can we make machine learning physics informed? So basically there are three approaches. So first one is the observational bias that amounts to training the model on data that reflect the underlying physical principle in the first place. That require quite a vast amount of data. So it's really difficult to get this amount of data. The next One is the inductive bias that amounts for designing specialized priors and architecture such that the certain physical principles are encoded inclusively in the model itself. And the third one is the learning bias that amounts to enforce physics through penalty constraint in the loss function during model training, and not directly through the architecture of the model, as we discuss here in the inductive bias. So among all the three, we are actually going to focus on the learning bias here. So a brief literature review. So ORD constructed the physics informed machine learning by using the prior knowledge, a systematic prior knowledge about the solution. So Cindy framework given by Bruton actually it's the Cindy framework is for the dictionary learning of the dynamical system. And Karpatne, he has proposed the physics guided neural networks. Wang and others, they proposed physics informed neural network for turbulence modeling. And more recently, Ricey and others, they proposed the PINN framework for solving PD and so on. This is just a brief literature survey. So the list is long. So in this talk, actually, I'm basically focusing on pins. Okay, so before moving pins, let's see the mathematical setup for the feed-forward neural network. So basically, we are going to use feed-forward neural network in PIN framework. So this is a typical feed-forward neural network with two hidden layers. Z is my input, and U is my output, and phi is my activation function. So the weights and biases in the kth layer are denoted by WK and BK, where the input is given by this term here, and the output at the kth layer is given by this term. So the L-1 hidden layer feed-forward neural network is essentially defined by this expression here, where in the last layer, the activation function phi is identity. So here K goes from 2 to L. And for the first layer, my input is defined like this. So the set of trainable parameters are defined by theta tilde, which consists of all the weights, biases, and this vector AK. So that actually represent the trainable parameter in the kth layer adaptive activation function. So basically here we are using adaptive activation functions. So references are given here. I'm not going to talk about adaptive activation in this talk, but basically we are introducing a trainable parameter in the activation function, so that along with the along with the weights and biases, we can also evolve the activation function, and we can get the optimal performance out of the network. So that's the idea behind the adaptive activation function. uh, Okay, so the output of the neural network is given by this expression here, where this term actually emphasizes the dependency of the neural network on the input vector z and the trainable parameter theta tilde. Okay, so physics informed neural network essentially defines a paradigm for bridging the physical models and the observational data. So basically we have a neural network here, and we are actually trying to match the output of the neural network with the given data. So that gives us a measurement loss. So given by this first term here. And at the same time, the output of the neural network should also satisfy the physical laws. So this is the physics informed neural network here, which uh, gives the PD loss given by this residual term. So this F is the residue, PD residue here. Uh, well, in this case, we are actually calculating all the derivatives in PD using the automatic differentiation, which is accurate till machine learning precision. Sorry, machine precision. So basically, our target is to minimize this loss function. So here, basically what we are doing, we are actually transforming the original PD problem into an equivalent optimization problem. And our job is to minimize this loss function. So the PINN algorithm aims to learn the surrogate U, which is U theta tilde, for the predicting solution U of the given PD by minimizing the loss function. defined here. So where my all the trainable parameters belongs to the view, which is a parametric space here. So there are many algorithms, optimization algorithm, which we can use to minimize this loss function, say Adam or LBFGS, which we generally use for the regression problem. So what are the advantages of PINN? So it can solve both forward as well as ill post inward problems. But then uh, there are few limitations. So here, due to high dimensional non-convex optimization problem, the accuracy of the method suffers. So basically, we usually get accuracy in the range of -5 or -6 L2 error. And the second problem here is compared to the traditional method, it takes large train. It needs large training time. So in this work, we are going to mitigate this second limitation, large training time, by using the domain decomposition approach. So what is domain decomposition? So basically you have an arbitrary shaped domain here, which you can decompose into a small subdomains. And then instead of a single pin in a complete domain, you deploy individual pin in all these subdomains. And basically then you are stitching these subdomains through some kind of an interface condition, which based upon the physics of the problem. So that's why we are incorporating this condition here in physics informed part. And correspondingly, you add the interface loss in your loss function here. So what are the advantages here? So uh, the main advantages of domain decomposition based pins are the parallelization capacity. We can parallelize easily all the subdomains because we have individual network there, and they have their own parameters. So we don't there is not much communication except along the interface where we are imposing the interface conditions. And a second thing is it can have a large representation capacity. So because you can choose the depth of the network as per the solution evolving. That means either you choose the network a priori, knowing that you have a complex solution in a particular subdomain, or you can use the meta learning to choose the network depth as you evolve in time, or as you develop your solution here. And the third advantage is we can adjust all the hyperparameters. As I said, we can use a meta learning to come up with all the hyperparameters. Uh, and the fourth one is we have seen that there is a reduction in error propagation in the domain, because we are actually adding an additional interface condition inside the domain. So that's the reason error can there is a reduction in error propagation. So, okay, before going further, let's discuss the errors involved in PINN framework. So basically, we have these three errors: the optimization error, generalization error, and the approximation error. So, so basically, F is my function space that can be represented by a chosen neural network. And the approximation error is the error between the exact solution and the approximated solution. So this is the approximation error here. And optimization error is the error between my solution at global minima defined by UG and the solution obtained at local minima defined by U tau, U suffix tau. And basically both optimization error and the approximation error, they do depend on the loss function as well as the network size. And this generalization error mathematically is just different between approximation error UA minus the approximate solution UA minus the solution at the global minima. So so the next point is generalization error does not depend upon the loss function or the network size, but it does depend on your number of residual points which you use to evaluate the residue of the PDE and their locations. So in case of domain decomposition based PIN, this is the scenario. So instead of uh, just single whole domain, we have subdomains which are connected. So that's why this blue double-headed arrow is there. And we have a function space for each network, depending upon the network size and the structure of the loss function. And we have optimization error, generalization error, and the approximation error for each network individually. So by choosing the network size in each subdomain, we can actually reduce the both approximation error as well as the optimization error, because they are all dependent on each other. And at the same time, we can also choose the number of residual points and their location carefully by dividing the subdomain. So uh, the domain decomposition based PIN can mitigate optimization, generalization, as well as approximation error efficiently here. So let's see the first method here, the conservative pins or CPIN for conservation loss. So in this case, these are the interface conditions. So we are actually seeing the QH subdomain here. So the first interface condition is given by the normal flux continuity. So it just you calculate the normal flux and you enforce the continuity of that flux across your interface. So Q is my domain under consideration, whereas Q plus are all neighboring subdomain which shares a common boundary with the subdomain Q. And second interface condition is the average solution continuity. So average solution is given by this term here, and we are enforcing the continuity of the average solution along the interface. So this condition will actually boils down to a solution continuity condition in case of solution which is smooth here. So the average of two solution is the same point here. But in case of a discontinuous solution, which we can expect, say for example, in a hyperbolic conservation law. So in this case, we are actually enforcing this middle point here. That's an average value. So we will see that was the advantage of enforcing this average value here. Okay, so let's see one example. So it's a viscous Berger equation, one-dimensional viscous Berger equation. And we have an initial condition which is very smooth. Uh, and these are the boundary condition here. So we are dividing the subdomains into four subdomains here, 1, 2, 3, and 4 slices along the x-axis. This is x and t domain, x and t axis, and we are numbering this subdomain from bottom to top. So it's a 1, 2, 3, and 4. And the corresponding network architecture is given here. So number of layers, number of neurons, residual points, number of residual points, and the adaptive activation function which we are using. So learning rate is given here, and we are using the Adam optimizer. So this is basically a pointwise error given here after 15,000 iterations. And the interesting thing here is to see the relative L2 error, how it varies with number of iteration. So we are doing here, we are using flux continuity, but the blue curve shows just a flux continuity term along the interface, and we are not using average term, which I discussed here. So this is the average term here, average solution continuity term. So that's the blue curve. And when we use average term, you can see the red curve here. So it actually accelerate the convergence much faster. And even after 15,000 iteration, we can see that the error is still decreasing. So this is just for the example. I wanted to show why this average term is important here. Okay, so our next example is 2D incompressible flow, Navier-Stokes equation. So basically, we are actually solving the lead-driven cavity flow here, and my domain is decomposed into a 12 subdomains. We can see the boundary condition here. So these three are the walls, and the top boundary is the lid, which is moving from left to right. So the network architecture in these 12 subdomain is given here: number of layers, number of neurons, and a number of residual points. And we are using tan H activation function everywhere in all the domains, and the Adam optimizer. So these are the results here. That's the velocity in x direction, the predicted velocity. That's the velocity in y direction. And this is the comparison of CPINN results with that of the GIA. That's the standard results we have, and they are matching pretty well. So these blue lines are it's the domain interface lines here. Okay, so next we are actually solving the inverse problem. So we have this following equation here, and with unknown parameters. So here beta, which is the wave speed, nu, which is the diffusion coefficient, and alpha, which is the dispersion coefficient. So these three parameters are unknown, and our aim is to identify these three parameters by using the viscous Berger equation. So basically, uh, 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 we are we got this data from the exact solution of viscous Burgess equation, and we have the same four subdomain, and we are initializing these values alpha, beta, and nu in all four subdomains separately. So you can see here, so these four curves: the red dot, the green, blue, and the magenta color here. So we are initializing these values differently in different subdomain, and as the optimization process starts, you can see that with number of iteration, it started converging to a single point, and then it is started converging towards the average value, the exact value here, which is shown by this dash black line. Uh, and you can see this exact values of alpha, beta, and nu, and the CPINN values given by the CPINN, which is quite accurate. So what next? So the thing is, it would be interesting if we can apply this domain decomposition strategy for every PD, and not necessarily for the conservation laws, as we have seen this in case of CPINNs. Uh, then it would also be interesting as well as efficient if we can apply domain decomposition in space as well as in time. So here answer is XPINN here. So let's see the interface condition. So for XPINN, we have the average solution continuity condition, which is same as before. And apart from that, we have the residual continuity condition. So basically, we are just saying that the residue at given by the one network at the interface is same as residue given by the neighboring networks at the same interface here. So with this way, you can actually decompose in time also. That's the idea here. So apart from the residual continuity condition, you can also uh, add the other continuity conditions depending on the orientation of the interface as well as the nature of the PD. So XPINN has all the advantages of CPINN, which we discussed earlier: parallelization capacity, representation capacity, and efficient hyperparameter adjustment, and also the reduction in error. And additionally, it has advantages over CPINN is it can extend to any differential equation, and not for just conservation laws. We can decompose in time also. So it's a space-time domain decomposition. And the final advantage is interface conditions are simple in the sense of implementation. So we do not need any normal direction here as in case of normal flux continuity condition, we need a normal direction. And if you have a very complicated interface in 3D, then calculating this normal can be cumbersome. And moreover, if you have a moving domain problem and your interface is also moving, then it will become very tedious to calculate this normal. So, but in this case, the residual continuity condition does not need any normal direction. So that's why in terms of implementation, it is very simple. Okay, so let's see a quick comparison between PINN, CPINN, and the XPINN framework. As I already discussed here, we cannot decompose PIN both spatially as well as temporally. Both CPIN and XPIN has parallelization capacity. It has large representation capacity locally, and we can adjust all the hyperparameters. In terms of applicability, we can use XPIN for any differential equation and not just for conservation laws. And interface conditions are all simple in terms of implementation. Uh, Finally, of course, we can decompose the time domain also. So as I said earlier, for moving domains, it will be really helpful if we use XPIN here. So let's see some problems. Say 2D problem. First is the 2D Poisson equation. It's a linear equation, and you can see the domain. My domain is it's really weird. It's arbitrary shape, and we are actually using two subdomains: subdomain one, sorry, subdomain two and subdomain three. I think it's not that visible, but yeah. So these are all non-convex subdomains, and if you see here, this is the exact solution, this is the predicted solution, and this is a pointwise error after 25,000 iterations. So you can see that the predicted solution is it's quite accurate here, and even with the kink or sharp corners along the interface, the XPIN can give better accuracy. We just use here 100 points along the interfaces, both interfaces. But if we increase the interface points, we observe that we get much low error here. So that's the loss function for subdomain 1, 2, and outer subdomain 3. So let's move on to our next case. So now this is again a viscous Berger equation, which we discussed earlier. So now you can see the subdomains here. This is again XT plot, and we are actually dividing the domain into two subdomains. So first one is a dolphin shaped subdomain 2, and the outer subdomain 1 given by this blue C or blue points. Um, yeah, this is the exact solution, and this is the predicted solution. And that's the L2 error in the whole domain. Okay, one more thing, we also plotted, well, no, I'm not showing here, but we also calculated the error only along the interface, just to see how well it is stitching. So we have seen that the error in along the interface is lower than total error. So for example, in this case, the uh, relative L2 error along the interface is in the range of -5, as opposed to the -3 error in the whole domain. So that shows that we are stitching the interface quite well. Okay, so the next example is the 2D compressible or Euler equations. So basically we are solving a oblique shock reflection here. These equation can satisfy the discontinuous solution. So our aim was to find out how well we can approximate these kind of solutions. So this is the my XT domain basically, and we have an inflow boundary condition along this left boundary, and the post shock conditions along this top boundary. So basically that creates a shock at this corner, which actually travel and hit this bottom wall here and then reflect it back. So, and you can see that we are dividing this domain into two subdomain. Again, a peanut shape subdomain 2 and outer subdomain 1. So here actually the shock is penetrating these subdomains and reflecting it back. Okay, okay. Apart from uh, the measurement loss given by the boundary conditions, not all, but just these blue points here, we are also enforcing the data coming from the Schlieren technology. So we use the data from Schlieren, which basically gives a first gradient of density. So we enforce that data in the vicinity of the shock wave. So these are the results here. That's the pressure term, density term, velocity in x direction, and velocity in y direction. So you can see this shock which is coming here, hitting the bottom wall, and then it is reflecting it back. And that's the comparison between the exact solution and the predicted solution at y equal to 0.5. So this is the line basically. Okay, so they are matching pretty well. So we captured this shock wave very well here. So let's see the multi-GPU implementation of CPINN and XPINN. So we are actually using a 2D lead-driven cavity case here, which we discussed earlier. So that's the computation versus communication time on CPUs. So we just use 100 points, residual points, and 20 interface points. So you can see here the computation time for computation and communication time for CPIN, and same for the XPIN here. Yes. Okay, sorry. In this case, both computation and communication time for CPIN is less compared to XPIN, because if you see the interface condition for XPIN is a complete equation, governing equation, and not just the fluxes, as opposed to the fluxes in CPIN case. So that actually takes we are actually calculating additional derivatives here, and that's why the computation and communication time is more in case of XPIN. But if you go to, oh, well, this is for CPUs. If you go to GPUs, we have increased the residue points to 4,000 and interface points to 200. So if you see here, the overall the total wall clock time for CPIN is again more compared to XPIN, but it's slightly more. If you see here, it's a 2 second, and here is 3 second here. Moreover, yeah, of course, but the communication cost is more because uh, we are actually finding the additional derivatives in the XPIN here. Okay, so this is the weak scaling plot for CPIN and XPIN. So basically we are increasing the number of subdomains here and the number of resources proportionally. So number of GPUs. So we have 4, 8, 12, 16, 20, and 24 GPUs. And well, in each subdomain, the number of data points are same. And if you can see here that we achieve perfect weak scaling both for XPIN as well as for CPIN. And of course, sample per second in case of CPIN is more compared to XPIN because of obvious reason which we discussed earlier. Uh, that's the strong scaling for on CPUs. So here, what the number of data points are same in the entire domain, and we are actually increasing the number of resources, number of GPUs, and we are actually trying to find out this speed up and efficiency for both CPIN and XPIN. So you can see that the speed up is more in CPIN compared to XPIN. And of course, efficiency is also more, at least, of course, not in this case, but yeah, most of the cases. And we overall, on an average, we hit the 80% of the efficiency here. So I guess these are the conclusions. So here we presented the domain decomposition based pin, so namely conservative pin and more general XPIN. Uh, they have all the advantages like parallelization capacity, large representation capacity, efficient hyperparameter adjustment. But compared to CPIN, XPIN decompose in time also. So that's the additional advantage of XPIN. We have also seen that both method maps implicitly on a CPU, GPU type heterogeneous computing environment. And of course, we have also shown that the computational time can be drastically reduced. Uh, uh, Especially, I mean, that's a promising approach for large scale and high dimensional problems. So one point here, future work is we are aiming for adaptive XPIN, because a priori we do not know. There are many questions. So for example, a priori we do not know how to decompose the subdomains in what shape. So that's another area. And second thing, we do not know how many interface points we need, but because we initially we are taking depending on the solution complexity and the curvature along the interface. And the third thing is how to choose the uh, parameters, that means the hyperparameters adaptively, that means using meta learning. So these kind of issues we are going to address here in the our future version, which we are working now. And I would like to acknowledge my contributors, Professor George Karniadakis and Dr. Khemraj Shukla, both from Brown University. And I'm open to the questions. Thank you.
Thanks a lot, Ameya, for this very interesting talk. We may have some discussion and questions.
Yeah.
There are a few questions raised in the chat. Redwan, I saw you had some questions. You may start.
Yeah, thanks. Hi, Amea, and thanks for the presentation. It was really interesting. Actually, I had two questions. So the first one, I mean, in each of the examples you shown, did you compare with a PIN on the whole domain? And what's the execution time gain in that case?
Well, we have not shown the comparison, but I would like to show one here. Just a moment. Just a moment. I'll stop this. So we have done comparison in terms of accuracy for PIN and XPIN, as well as also CPIN. So I'll show you just a moment. I'm downloading the paper. I don't have in this new computer. So